This video is about one of the most ubiquitous concepts in all of modern mathematics, which is that of a function. The definition of function is actually quite complicated. For us, a function is going to be made up of three separate parts. So a function f consists of a set x called the domain of f, a set y called the codomain of f, and a rule which associates to each element little a in x a single element called f of a in y. And there's some notation which summarizes these three parts of the definition of a function. When we write f colon x and then a right arrow and then y, that means that f is a function whose domain is x and whose codomain is y. Now, functions are something which is very familiar to you, even though they might not have been expressed in precisely this form. So let's look at some familiar examples. We'll begin with a function f from the real numbers to the real numbers, with the rule being that f of a number x is equal to x squared. And that's an example of a function whose domain is the real numbers and whose codomain is the real numbers. And it's also an example of how we commonly describe functions. So a very common way to describe a function is by giving the rule via a formula. So saying if you give me any particular input, any particular element x of the domain, then here's what the output f of x is, x squared. Another example would be g from the set of real numbers to the set of non-negative real numbers. So if you've not seen this notation before, let's just have a little arrow here. What I mean by square brackets 0, comma, infinity, round brackets, that's supposed to be, in set builder notation, all the real numbers which are greater than or equal to 0. So we could say x in R such that x is greater than or equal to 0. That's the meaning of this interval notation. If you're not familiar with it, go and Google interval notation, because it's very, very common. Okay, so here g is a function whose domain is the real numbers, its codomain is the non-negative real numbers, and whose rule is that g of a element x in the real numbers is x squared. And this really does define a function with this domain and this codomain, because no matter what real number x is, x squared really is an element of that codomain. And you'll see it was part of the definition of a function that for each a in the domain x, f of a had to be an element of the codomain y. Okay, next, function h is a function whose domain is the set containing 0 and 1 and whose codomain is the integers. G of 0 is 24, g of 1 is minus 777. So I'm just trying to illustrate here that a function doesn't have to be given by some familiar formula, by some formula with mathematical symbols in it. A function can be absolutely anything at all. It does not have to have some definition with familiar mathematical functions in it. Any kind of rule which associates to each element of the domain an element of the codomain defines a legitimate function. Finally, our last example is actually a kind of universal example. For any set x, there is an identity function from x to x. So an identity function written id subscript x, which has domain x and codomain x, and whose rule is that it doesn't do anything. So it associates to each element little x in big X the element little x in big X. So it doesn't do anything. All right. Now, as I said, functions are absolutely everywhere in mathematics. So unfortunately, that means there is a lot of different terminology associated to functions. In particular, lots of terminology that means the same thing. So if you talk about a function and if you talk about a map, those mean exactly the same thing. If somebody says map, they mean function. Next, there's a quite common piece of vocabulary that we use to talk about functions, which is inputs and outputs. So we often refer to this element f of x, which has to be associated to each element little x of the domain, as the output of f given the input x. As an example, if we have the function f from R to R, given by the rule fx equals x squared, then you might say that given the input minus 1, the output of that function is 1. Okay, another bit of vocabulary we use is sends or maps to. When we say f sends x to y or f maps x to y, all we're saying is that the output of f, when you give it the input x, is equal to y. So sends or maps to is just another way of talking about what the output of f is for a given input. Another piece of vocabulary for the same thing is that when you talk about the image of an element of the domain of a function f, what you mean is just the output for that input. So the image of x under f just means f of x, the output of f given the input x. And finally, although I'm sure there's more vocabulary which I've not thought of, but another very common thing is when we talk about applying f to x. Well, again, what we mean when we talk about applying f to an element x in its domain is just coming up with what is f of x. Okay, but there's another useful tool associated to functions, which is function diagrams. So there are lots of concepts associated to functions which we're going to discuss, and it helps in discussing those to be able to draw pictures of what we're talking about. In particular, there's a particular style of diagram that I'd like to use to talk about functions. So if we have a function f from x to y, we often draw a diagram of f. Where we'll draw the elements of the domain x on the left, so these dots are supposed to be elements of x, and elements of the codomain y on the right, and then arrows to indicate what f does. So a function f must associate to each element of its domain another element in its codomain. So we'll draw an arrow to show which element of the domain is associated to which element in the codomain. So the rule means there must be an arrow starting at each element of x. So perhaps a function might look like this. As a concrete example, let's say if we had f being the function from the integers to the integers given by f of x is equal to x squared, then, I mean, of course we can't draw all of the diagram for this function because there's infinitely many integers, so I don't have time to draw all of them. But we might have, let's give them actual names, we might have things like 2, 1, 0, minus 1, 2, and so on here in our domain, and in our codomain the same things. And we can at least draw the images of some of those elements of the domain. So 0 would go to 0, and minus 1 would go to 1, and 1 would also go to 1. But 2 would go to somewhere up here. It goes to 4, which is somewhere up there. And you can see I've missed the minus sign off down there. That would also go to somewhere upstairs, the same place as this one. So these diagrams can actually be quite helpful in understanding some of the concepts and some of the special types of functions which we're about to introduce in the next video. So moving on, here's a question about when two functions are equal. Let's think about the two functions f and g, which have the same domain, so 0 and 1, and the same codomain, 0 and 1, but two rules which look slightly different. So the rule for f is f of x is equal to x squared minus x. And the rule for g is just that g of any input x is equal to 0. So let's look at what f and g actually do. So here I'm going to draw f in blue here. Let's work out f of 0. That's 0 squared minus 0, which is 0. And f of 1 is equal to 1 squared minus 1, which is 1 minus 1, which is 0. Okay, so f of 0 is 0. And f of 1 is 0, and of course g, well, by definition, g of 0 is 0, and g of 1 is 0. So we have a question now, which is that is f equal to g? Because on the one hand, they seem to do the same thing. F of 0 is 0, g of 0 is 0. f of 1 is 0, g of 1 is 0. But on the other hand, the rules actually look different. They simply have different formulas associated to them. So we've got to make some kind of decision here. Like, we have to make a definition about when two functions are equal. We can't appeal to any other concept. We have to actually make our own definition about this. And here's the definition that we make. We define two functions to be equal. So this really is a definition. If and only if, number one, they've got the same codomain. Number two, they have the same domain, and we're going to call that domain x. And number three, f of x is equal to g of x for all x in the domain. So in this case, those two functions would be equal because these properties were all true. Our functions f and g on the previous slide had the same codomain, which was the set containing 0 and 1. They had the same domain, which was the set containing 0 and 1. And f of x and g of x were equal for all x in x, namely f of 0 was equal to g of 0, and f of 1 was equal to g of 1. So, according to our definition, they had the same domain, same codomain, and their outputs were always equal, so f and g were equal. So this is one, there are other possible definitions of equality of functions, but for us this is the right definition, and it's the standard definition in mathematics. So we need to keep this in mind, because it means that two functions can actually be equal even if their rule might look superficially, it might look different. Okay, moving on to a new topic, we're going to talk about composing functions. So let's say we have two functions. I'm going to write at the top here. Let's say we have some sets x and y and z. So I'll draw a slightly different kind of diagram where I draw arrows between these functions, between these sets rather, and I label those arrows. So the first one I'm going to label f, to indicate that f is a function whose domain is x and whose codomain is y. And I'm going to draw an arrow and label it g to indicate that g is a function whose domain is y and whose codomain is z. So that's the situation we're talking about in this definition. F is a function from x to y, and g is a function from y to z. And then the point of the definition is that you can now form a new function whose domain is x and whose codomain is z, and whose rule is start off with an element of x, and then do f to get into y, and then do g to that to get into z. And that's called the composition of g and f, and it's written in this way with a little circle. Okay, so let's read this out properly. A function, suppose you have a function f from x to y and g from y to z. Then the composition of g and f, written g, then a little circle, then f, is the function whose domain is x and whose codomain is z, and whose rule is that the output of g composed with f, when you give it an input little x, is g of f of x. And that's something that makes sense because f of x is an element of y, so you can apply g to that element of y and get an element of z. So we really have here defined a function with domain x and codomain z. Another way to state this rule, the rule for the function g composed with f would be do f and then do g. And it's important to remember that it's that way round. So this can be a little bit confusing because we write g on the left and f on the right, but the rule is do f and then do g, not do g and then do f. That doesn't even make sense, because if you do g, you get an element of z, and you can't apply f to an element of z. F takes inputs from the set x, and maybe x and z are different. So it's important to remember that this rule is do f and then do g, and that looks a bit weird because we write g on the left and f on the right, and we read from left to right. So let's look at an example of a composition of functions. Here we have a function f from r to r, f of x is equal to x plus 1, and we have a function g from r to r, where g of x is equal to x squared. So these functions have the correct layout for us to be able to compose them to form their composition, because you have the real numbers and then the real numbers, and f goes from the real numbers to the real numbers, and g goes from the real numbers to the real numbers, so it's possible for us to form the composition g composed with f, and also we could do that the other way round if we wanted, so we're actually going to do both. So f composed with g of x will be the function whose domain was the real numbers, whose codomain was the real numbers, and whose rule was that f composed with g of x was f of g of x. So that's f of x squared, which is x squared plus 1. On the other hand, we could do the composition the other way round. G composed with f of x is g of x plus 1, which is x squared plus 2x plus 1. So let's notice that g composed with f and f composed with g were different functions. In this case, the rules don't just look different, they genuinely are different. Because, for example, f composed with g of 1 will be equal to 2, and that's not equal to g composed with f of 1, which will be 4. So not only do those rules actually look different, they genuinely do produce different outputs for the same input. So even when both of the compositions f composed with g and g composed with f make sense, they might be different. So function composition is not commutative. F composed with g might be different to g composed with f, even when both of those things make sense. But it does have the associativity property that we met before. Specifically, let's say you've got three composable functions, f and g and h. What I mean by composable is that we have the following situation. So we have x, y, z, and w, 4 sets, and f goes from x to y, so f has domain x and codomain y, g goes from y to z, and h goes from z to w. In that case, I can compose f and g, and I can compose g and h. And I could even compose f with g composed with h, and f composed with g with h. So that raises a question. Are those two things the same? And what the theorem says is that actually they are the same. So in this situation where f goes from x to y, g goes from y to z, and h goes from z to w, then the two compositions, h composed with g composed with f and h composed with g composed with f, are equal as functions. So if I want to prove this is true, you'll remember that I have to check three things, because the definition of function equality involved three things. Two functions were equal when they had the same domain, same codomain, and the same input, same output for every input. So for sure these two functions, this one and this one, have the same domain, because the domain is x in both cases. And for sure they have the same codomain, because the codomain is w in both cases. So both functions are functions from x to w. What we need now to do is argue that they have the same output for every input. So we pick an arbitrary element of the domain, so an arbitrary little x in the domain capital X. And then we work out what those functions do to an element of x. We have to keep our head here because there's lots of circles and brackets floating around. So let's just take it slowly and work out what's going on. So the composition of h with g composed with f is the function which sends x to h of g composed with f of x. So that is what I've written right here. But now g composed with f of x is just g of f of x. So what we get here is h of g of f of x. That's the output. Well, all right. Well, now let's unpick the other definition. So the right hand of those two functions in the statement of the theorem. This time we've got h composed with g in brackets composed with f. We want to know what that does when we give it the input x. Well, again, the definition of h composed with g composed with f is it's the function whose output given an input x, is h composed with g of f of x. So that is what I've written on the second line. But I mean, this is just, by definition of h composed with g, h of g of f of x. All right, well, that's the same thing as we got before. So for any input, those two functions have the same output. They have the same domain, same codomain, and they for each possible input, they have the same output, so they're equal as functions. And this associativity property is super useful. We end up using it all the time. It's very, very, very important property of function composition. Okay, final slide. Let's think about composing with the identity function. So remember that if you had a set x, then the identity function, which we wrote as id and then subscript x, was the function whose domain was x and whose codomain was x, and the rule was it didn't do anything. So if you give it an input little x, then it just gives you back that same little x as output. And what this lemma says is that, as expected, if you compose with the identity, so if you compose a function f with the identity on either side, then you just get that function f back again. Specifically, if you have a function f from a set x to a set y, then you can compose f on the right with the identity on x, and you can compose f on the left with the identity on y, because, I mean, just think what's going on here. You have a diagram like this. F goes from x to y, the identity on x goes from x to x, the identity on y goes from y to y, so I'm free to compose the identity on x with f, and I'm free to compose f with the identity on y. So in this case, what the lemma says is that f composed with the identity on x is equal to f, and the identity on y composed with f is equal to f. And this really is just a matter of understanding the definition of composition of functions. So let's just think about the first of those equalities. F composed with x for sure has the same domain as f, namely x, and the same codomain of y, and the same codomain as f, namely y. We're just looking at this part of the diagram, so this part here. So the composed function identity on x composed with f would have domain x and codomain y, just like f does. So f composed with the identity on x has the same domain as f, namely x, and the same codomain as f, namely y, and they also have the same output for every input. Because if you think about f composed with the identity evaluated at an input little x, then by definition of composition, that's f of the identity of little x, and by definition of the identity, that's just f of x. So f and f composed with the identity agree on every input. They have the same domain, they have the same codomain, so they are equal as functions, and similarly, the other equality is true.